Hello. Hello, everyone. If I could get some comments on how assignment 8 is going. Any particular difficulties that you're facing? Can you hear me? Oh. Okay. So can I get some comments on how assignment 8 is going? So any particular difficulties you're facing? Okay. Well, I'll start the webinar, and if okay, I'll start the webinar, and if you have some questions, do let me know. Okay. So today I'm going to show you the art of analyzing functions, analysis of functions. So this is the second to last section in the assignment. So for analysis of function, also finding its primary features, including zeros, where y is 0, the intercept, obviously, where x is 0, the asymptotes, the stationary points and monotonic intervals, inflection points, domain, and range. Okay, so you don't have to do all of them in order to analyze a function. The result of analyzing a function is usually a graph. Yeah, so of course you can use Desmos to draw a graph, and this gives you an idea, but a deep analysis of functions is incredibly useful in how you understand functions, how you understand how they work, and specific features. So we'll start with a simple function, and we'll start with the domain. And domain is quite simple here because there are no restrictions on x. So domain is all real numbers. The range is the possible values of y. So are there any limitations on y? Well, we can we already know what x cubed looks like. So this is a transformation of x cubed. So probably the range is from minus infinity to plus infinity. So all real numbers. How to check that? Well, you can see what happens if x becomes really big and positive. If x becomes really big and positive, this becomes really big and positive as well. So plus infinity. And when x becomes very, very small, so sorry, very negative and large, very large and negative, this number becomes negative. Yeah, so you can test it. Put minus 1 million into the function, and it will give you a negative value. So therefore, the range is also all real numbers. Okay. Now, because the domain is all real numbers, there are no discontinuities of the graph. There's no points where the graph does not where the graph breaks, does not exist. So there are no asymptotes, no vertical asymptotes. Vertical. I will show you how to find vertical asymptotes later on. If you don't understand why, just believe me for now. There are no vertical asymptotes. Are there any horizontal asymptotes? Well, not really. You can see that the graph, as x becomes really big, it goes really high up, and when x becomes very negative, it also becomes very very negative as well. So no horizontal asymptotes, no horizontal or slant asymptotes. Next, let's do zeros. Well, to find the zeros, we need to solve the equation 2x cubed plus 3x squared minus 1 equals 0. So how do we solve this? Well, we can guess a solution. Yeah, we can guess a solution. So x equals minus 1 is a solution. It's very easy to check. Yeah, so you substitute minus 1 and you will see that, in fact, this minus 1 is a solution. So in order to find the other solutions, I'm going to do 2x cubed plus 3x squared plus 0x, because there's no x here, minus 1. And I'm going to divide it by x plus 1. I'm dividing it by x plus 1 because from the factor theorem, that means it is, so x plus 1 is a factor. Okay. Are you familiar with this, or is this completely new? Please comment in the chat. Is this completely new to you, or you're already familiar with it? Familiar. Oh, good. Yeah, that's fine. So I won't go into much detail about this. So I divided by 2x squared, 2x cubed. Actually, you know what? Since you're familiar with it, I'm going to show you another way of doing it. I'm going to show you another way of doing it. So what you need to do, because you need to factor out x plus 1. You need to factor out x plus 1. So what you need to do is, so 2x cubed, in order to factor out x plus 1, you need this to be 2x squared. And that's what we're going to do. So we're going to get 2x cubed plus 2x squared. Now, well, I can't change this, so I have to write plus x squared. Plus x squared. What am I missing here in order to factor out x plus 1? So this can be factorized, and one of them, yeah, plus x. Now, because there's no x here, I'm going to write minus x and minus 1. And then I'm going to group them like this. Now this is going to be like this, equals. I'm going to factor it out. So here it's 2x squared is the common factor, 2x squared, open bracket, x plus 1, plus, here's the common factor is x plus 1. And here is minus x plus 1. So this can be written as, this can be written as x plus 1, open bracket, 2x squared plus x minus 1. And of course, because you can factor out the other bit, the other half, so it's going to be x plus 1, and then 2x squared plus x minus 1. As a matter of fact, it has two solutions. One of them is minus 1, so it's going to be x plus 1, and the other one is going to be 2x squared plus x minus 1, so it's going to be plus a half, so it's going to be 2x minus 1. Right. So we have two zeros. The zeros are x equals -1, and x equals a half. Now we're interested in the critical points or the extreme points. This is where the derivative is 0. So we find the first derivative is going to be 6x plus 6x squared plus 6x, and this is equal to 0 when x, so stationary points, so x, if you solve this equation, x is either 0 and x is -1. X is 0, 0, x equals -1. This is useful. So I hope you all understand how I did this. So 6x, x plus 1 equals 0. So x equals 0 or x equals -1. Stationary points and points of inflection. So we find the second derivative. So y second derivative. So we differentiate the derivative. So it's going to be 12x plus 6. And this is equal to 0 when x is inflection point x, well, possible inflection point, possible inflection point, x equals minus a half. All right. What else? Well, we need the intervals of of increase and decrease, and I'm going to show you a short way of doing it. Okay. I'll just solve here. So here, 6x squared plus 6x is, I'm interested where the function is increasing. When the first derivative is greater than 0, the function is increasing. So it's monotonically increasing. And so that's 6x x plus 1 is greater than 0. So f of x is increasing. When? Well, I hope you know how to solve quadratic inequalities. So here, it's greater than 0 when x is greater than 0, or when x is less than -1. Okay, you can see it from here. Then inflection point. So we need to find where the function is convex and where it's concave. That is, so 12x plus 6 greater than 0. So when it's greater than 0, it's convex. Convex if that is convex when x is greater than -1/2, and concave, and therefore it's concave when x is less than -1/2. Is everyone following? Is everyone following so far? So what I did is I found the first derivative. Therefore, I found where the function has stationary points. And I found where the function is increasing. I found where it's well, therefore I found it's where it's decreasing. I'll add it. F of x is decreasing. Please do ask me if there's anything you don't understand. Please do ask me. When x is when x is greater than -1 and less than 0. Okay, right. Of course, you can do this function in a much easier way, but I'm showing you the principle. I'm showing you the way you approach any function, not just the simple ones. Okay, now you draw a line. Tricks when remembering when a function is concave. Well, it's concave when the second derivative is negative. A trick. Well, the only trick I can think of, so the second derivative is negative, is concave. It looks like a cave. Yeah. Concave. And convex is when the second derivative is positive. Second derivative is positive. You can think of, I don't know, concave. It's like a sad word. It looks that looks like a sad face. Concave. Cave looks like a cave. Yeah, like an entrance to a cave. It looks is convex, and convex sounds like convex. I don't know. You can use that if you want. Right. The next, you draw a line. You draw a line, and you put all the points that you found interesting. So first of all, the zeros. So -1 and half. Then the stationary points, 0 and -1. So 0 is roughly here. -1 is same place. And then you have possible inflection point. This is -1/2. Right. There are no more interesting points here. So what you do next when analyzing a function. Sorry for the mess. I'm without my pad. Right. So you write down f of x. So the zeros are -1 is a 0 of a function. Is 0 of a function, and a half is a 0 of a function. So if a half is a 0 of a function, to the right of 1/2, it's going to be positive. And you can easily check that. For any value more than a half, the function is going to be positive. For the values here, it's going to be negative. Because since there are no zeros here, this is still negative. And now we come to the tricky bit. So it seems like the function should become positive here, but it's not. You can easily check a very negative number, and you will see that the function is in fact going to be negative. So the function is negative everywhere, except when x is greater than a half, and except when x is -1. Then the second derivative, sorry, the first derivative. Function is increasing. So increasing, decreasing, and increasing. Then the second derivative. So it's convex here. So the second derivative is positive, and here it's negative. And now the thing that I enjoy the most. So here, the function is positive. It is increasing, and it is convex. Therefore, I draw the function like this. Convex, that means it's bent downwards. It's increasing. Yeah, it's increasing. And it's positive, so it's above the x-axis. Now here, on this interval between 0 and a half, the function is negative, but it is increasing and it is convex. So it's going to be like this. But now it's below the x-axis. And just all right. Now the function is negative. It is decreasing, but it is convex. So it's going to be like this. Here, the function is negative. It's going to be decreasing, but it is concave. So the function looks like this. It's decreasing, it's negative and concave. And finally, on this interval, the function is negative. It is increasing, but it is concave. So it looks like this. And already we can see what the function looks like. All we need now is to find where all we now need is to find where all the values at the critical points. Okay. So, I mean, yeah, it is useful. So y is, so when it is 0, y is -1. When it is, you can actually, yeah, when it is -1/2. So when it's -1, it's 0. When it's 1/2, so it's 1/4 plus 3/4 is 0 again. And when it's -1/2, so it's -1/4 plus 2/4 plus 3/4, so that's 1/2. 1/2 minus 1 is -1/2. -1/2. Right, so this is extra. You don't always have to do this. So then we just draw a sketch. We draw a sketch. So 0. Let this be 1. Let this be -1. This is -1/2. This is 1/2. This is 1/2. And it is 0, so it goes through this point. When it is 0, it's -1, so it goes through this point. And when it's -1/2, it's -1/2, so it goes through this point. When it is 0, it's when it's 1/2. Oh, sorry, when it's 1/2, it's 0. Not when it's 1. When it's 1/2, it's 0. And when it's -1, it's 0 again. And then we look at this graph. So we look at this part. We look at this part. So the function is increasing, but it is concave. Then it's decreasing and it is concave. Okay. Then it is decreasing, but it is convex. And then it is increasing, but it is convex. And it keeps increasing and it is convex. Okay. This is a very elaborate method, yes, of analyzing functions. But this gives you a lot of information about the function. So, I mean, a good idea, one of the things you can do is just start with this. You can start with this table, because this table is amazing. And now let's check if we are correct. So y equals 2x cubed plus 3x squared minus 1 plus 3x squared minus 1. It is. It does look like we were correct. You can see this is quite accurate. We got the point of inflection correct. The point of inflection is indeed minus half here. And then we got the extreme points. Right. Any questions? Any questions? Okay. Right. So the next one. The next one, well, actually, we spent 25 minutes on the first one. There's no way we can do nine problems today. I was a bit ambitious. So here, just a few features of this graph. It is very useful to note that this function is even. This is an even function. Function is even because f of minus x is equal to minus x to the power 4 minus 10 minus x to the power of 2 plus 9. And if you simplify that, it actually becomes, well, minus x to the power 4 is x to the power 4. And minus x squared is x squared. It's the same thing. Minus x squared and x squared are the same thing. So it's minus 10x squared and plus 9. So as a matter of fact, f of minus x is equal to f of x. Yeah, so f of minus x is equal to f of x. So the function is even. What does that mean? Well, it means that the graph is going to be symmetrical, and the y-axis is going to be the line of symmetry. So the graph will have a line of symmetry. Let's check. So y is equal to x to the power 4 minus 10x squared, 10x squared plus 9 plus 9. And we hide this one. And you can see that this graph definitely has a line of symmetry, and this is a vertical line of symmetry, and this is the y-axis. Okay. All right. Let's see this one. So domain. Are there any restrictions on x? Well, no, actually. So what are the restrictions? Well, you can't divide by 0, but the bottom, the denominator is never 0. Yeah, denominator. So all real numbers. Now with the range, that's quite interesting. So to find the range, well, x squared is greater or equal to 0. That means 1 plus x squared is greater or equal to 1. So 2 divided by 1 plus x squared is, on one hand, is going to be less than or equal to 2. But on the other hand, it's a positive number, so it has to be greater than 0. Greater than 0. So range x in from 0 not inclusive up to 2 inclusive. This is another way of writing that 0 is less than x, less than or equal to 2. Okay, so this notation means, so round bracket means not including, 2 means including. Okay, then we need to look for asymptotes. Asymptotes. So how do we look for asymptotes? Well, we find the limit as x tends to plus infinity, of f of x. So what happens when x becomes really, really big? Can somebody help me? 2 divided by 1 plus a really, really big number. It becomes infinitely small. It becomes 0. Well, it's not y equals 0. It's the limit is 0. Okay, and that means that y equals 0 is a horizontal asymptote. On the right. Similarly, we can do limit, but you can also use you can also notice that this function is even. This function is even as well, so it's going to be symmetrical. So if y equals 0 is an asymptote on the right, it's going to be an asymptote on the left as well. But for the sake of it, we just say limit. So as I said, analysis of function is a form of an art. So there's no one solution. Yes, so when it's to minus infinity of f of x, so you substitute a very large negative number. So it's 2 divided by 1 plus a very negative number squared is also 0. So you can say same on the left. Now there are no discontinuities, so there are no vertical asymptotes. No vertical asymptotes. And well, okay. Let's find the first derivative. First derivative of x is, so the just write y prime. So it's going to be the derivative of 2 or 1 plus x squared prime. So the derivative of that equals minus 1 to the power minus 1 and prime. So we use the chain rule here. So it's going to be the derivative is going to be 2, 1 plus, so minus 2, 1 plus x squared to the power of -2 multiplied by the derivative of the internal function, which is 2x. So this simplifies as minus 4x divided by 1 plus x squared and we are interested where it's positive, so this is greater than 0, and because the bottom part is a positive number. Look, the bottom part is always positive. It's 1 plus x squared, that's positive, squared again, that's a positive number. So we don't really care about this. We're interested where this thing is positive or negative because there's a minus. And this thing, we got, that means minus 4x is greater than 0. So x is less than 0. So increasing when x is less than 0, and decreasing when x is greater than 0. That's an obvious one. Second derivative. Now, you don't always have to do such an in-depth analysis. Yeah, so I mean, depends on the question. Second derivative. So to find the second derivative, I'm going to use the quotient rule here, I guess, to find the second derivative. So derivative is -4, open bracket, 1 plus x squared, close bracket, squared, minus, well, minus is going to be plus in this case, 4x, and then the derivative of that. So there's going to be 2, so multiplied by 2, open bracket, 1 plus x squared, close bracket, and multiplied by 2x, divided by something, 1 plus x squared to the power 4 in this case. And we're interested where this is greater than 0. So that's tricky. So 1 plus x squared is a common factor. So 1 plus x squared is a common factor. That's nice. So we get -4, open bracket, 1 plus x squared, plus 16x squared. Sounds right. So 1 plus x squared is a common factor. We ignore the denominator because we're not interested in that, and that's greater than 0. So the 1 plus x squared is positive, so we can divide by that. So we don't care. We're only interested in that. So it's going to be -4x minus 4 -4x squared. Okay, I have to. Okay, just a tad more detail. For 1 plus x squared plus 16x squared is greater than 0. So I've ignored the 1 plus x squared because it's a positive value. The positive cannot affect whether the whole expression is positive or negative. It's just a positive number. So we divide by 1 plus x squared. We're allowed to do this. So divide by 1 plus x squared. Range, oh, of course, yes, sorry. range y. Thank you. All right, so now we open the brackets, so it's -4 minus 4x squared plus 16x squared is greater than 0. So it's going to be 12x squared. 12x squared is minus 4 is greater than 0. Divide by 4, so 3x squared. 3x squared minus minus 1 is greater than 0. So you can find the critical points. The critical points is, well, I'm going to factorize it. Greater than 0. So it's going to be square root of 3x minus 1, and square root. I'm using the difference of two squares. I'm using the formula here. I'm using this formula. A squared minus b squared is equal to a minus b, a plus b. Cube root of 3, so square root of 3x plus 1. And so this is positive when x is greater than 1 over square root 3, or x is less than minus 1 over square root 3. Okay, so the function is convex when for these values. The function is convex. All right, and in a similar way, we draw a table. So interesting points. Well, 0 is definitely an interesting point because that's a stationary point. 0 is a stationary point. Then x, then there are no other interesting points except 1 plus square root of 3. So 1 over square root of 3, that's an inflection point, and minus 1 over square root of 3. So these points so x equals that and x equals that are inflection points. Inflection points. And now what you need to do is you need to analyze. So f of x, as we saw that it's always positive. The function is always positive. It's never negative. Then the first derivative. So here it is positive, then it becomes negative and negative. And then the second derivative, so we saw that it's positive when x, so it's positive, negative, negative, positive. So it's positive when x is, basically what we do is we split the domain into intervals, and we see what happens to the function and the derivative and the second derivative on each of these intervals. All right, and then we can see that here the function is increasing and it is convex. So it's going like this. The function is positive. It is increasing, but it is convex. So it's like this. Here the function is positive, is decreasing, and it is concave, like this. So you see how the arrows are bent, and here the function is positive, it is decreasing, and it is convex. So it's going like this. So we can already see, kind of figure out, even especially if we draw the arrows like this, we can already see the shape of the graph. So this is almost a sketch. Then what do we need? Well, we need you need to find the value of the functions at these points. So when x is 0, y is 2. When x is minus 1 over cube root of 3, so it's 1 plus third, so 2 oh no, it's going to be 1 plus a third, that's 4 thirds. 2 divided by 4 thirds, that is going to be 6 divided by 4, is 1.5. Y equals 1.5. All I'm doing is I'm substituting these values, and here y equals 1.5. So these are the points of inflection. And now we draw the graph. Well, we draw the sketch of the graph, obviously. So x, y, and we have 0 and 2, 0 and 2. Then we have the asymptote. Then we have the inflection points, which is minus 1 over square root of 3 and 1.5 here. A symmetrical point here on the other side, 1 over square root of 3, 1.5, 1.5, and we have the asymptote. Usually we draw the asymptote is y equals 0. Usually we draw the asymptote as a dashed line. And we draw y equals 0. This is the asymptote. And just looking at this, we can already sketch quite a decent graph. It's a point of inflection. Right. And just in case, y equals fraction 2 divided by 1 plus x squared. Here it is. Okay. Okay, that's been another 20 minutes. Okay, this one, just let me see what else do we have here. I won't be doing number 4 because there are no asymptotes, or at least no interesting asymptotes. I want to do, I'll do problem, yeah, I'll do problem 5. Okay, I'll do problem 5. So here, so there are values that need to be excluded. Oh, no, actually, no, sorry. Problem 5 is not very interesting. Sorry, not this one. Straight to problem 6. So domain, x is not equal to 2 plus minus 3. Because if x is 3 or minus 3, the denominator is 0. So automatically, these are candidates for vertical asymptotes. X equals plus minus 3 are possible vertical asymptotes. Good. The range. Do we really need to find the range here? It's going to be quite tricky. I'm going to skip the range because I can't see an easy way to find it. Yeah. Otherwise, I just might spend hours or spend 20 minutes finding the range. Why would I do that? Okay, finding the first derivative will actually help me to find the range. Range question mark. Then immediately I can do so then yeah, let's deal with asymptotes first. So asymptotes. So as the limit as x tends to 3 of f of x, and as you can see, so it's 2 plus x divided by 3 squared minus 9. It's going to be division by 0. But what if it's not? What if it's a number which is very close to 3? So for example, if you take 2.9999, you will see, well, it's actually infinity. And actually, when it tends to minus 3, it's also infinity. So in fact, and you can check that by taking values of x which are very close to 3, that it actually does tend to infinity. So x equals plus minus 3 are vertical asymptotes. Usually, if the denominator is 0, then it's a vertical asymptote. I can give you an exception. So for example, y is equal to x minus 3 squared divided by x minus 3. Now it seems like this graph has a vertical asymptote at x equals 3, but no, actually it doesn't, because you can simplify it and it becomes just x minus 3, which does not have a vertical asymptote. So this type of graph does not have a vertical asymptote. It's easy to see because it simplifies. If it doesn't simplify, when the denominator is 0, that's a vertical asymptote. Horizontal asymptotes. Well, we need to find the limit when x is plus infinity, and of f of x. So what happens when x becomes really, really big? Well, it becomes very, very small, but positive. We're going to write it as plus 0. That means very small, but positive. And the limit of x that tends to minus infinity of f of x equals, you can see that it's going to be minus 0. So very small, but negative, very small, negative. That means that y equals 0 is a horizontal asymptote. Horizontal asymptote on both sides. Then we find the derivative. Y is equal to y prime is, okay, we need to use the quotient rule here. So x plus 2, so it's going to be 1 multiplied by the derivative of the 2x minus x, oh, what am I doing? Sorry, 1 multiplied by x squared minus 9 minus x plus 2, and then derivative of 2x plus 9, so multiplied by 2x all over x squared minus 9 squared. So that is, we can simplify that. So x squared minus 9 minus 2x squared minus 4x all over x squared minus 9 squared equals, well, we're interested where this is positive. We're interested where this is positive because we're interested in where the function is increasing. But yeah, where this is positive. And right, the denominator is always positive. Well, at least the denominator is always non-negative. Denominator is non-negative, but the numerator, so x squared minus 2, so it's going to be minus x squared minus 4x minus x squared minus 4x minus 9 is greater than 0. So I'm going to write x squared multiplied by minus 1, so plus 4x plus 9 is less than 0. Solving that, so two numbers which multiply to 9 and add to 4. Oh, there's no such numbers. Oh, okay, that makes life easier. The discriminant is less than 0. Therefore, there are no solutions. The quadratic equations have no solutions. Therefore, the second derivative, the derivative is always negative. So this is never true. This is never true. Never true. As the discriminant is less than 0. Therefore, f prime of x is always decreasing. That's an important piece of information. I'm going to skip the second derivative here. I don't think there's going to be anything useful there. And I'm just going to jump straight into the table. Right. And so this is x. So interesting points. There's one 0 over function. Is x equals minus 2. So 0 is x equals minus 2. X equals minus 2. -2, and it's -3 and 3. We know that the function is always increasing. It was decreasing, sorry. And also that when it's y equals 0 is an asymptote. Y equals 0 is an asymptote. So the function is going to go, so f of x, here it's going to be positive. Aha, interesting. So here the function is going to be negative. The function is going to be positive and negative. How do I know this? Well, it's easy to check. You just find f of 4, and it was going to be positive. So on this interval, from 3 to plus infinity, is going to be positive. Take any number on the interval from -2 to 3, for example, f of 0. F of 0 is going to be 0 plus 2 divided 0 minus 9. It's going to be negative. And any number between -3 and -2 is going to be positive, and any number between -infinity and -3 is going to be negative. Then we have the first derivative, and the first derivative is always negative. We've established that. All right, so the function is now, because I didn't do the second derivative. I didn't do the second derivative. I don't know when the function is convex or concave, but I know that the function is negative and decreasing here. So I draw a straight line down here. The function is positive and decreasing here. And the function is negative and decreasing here. And the function is negative and decreasing here. Okay. And then you start sketching. And it might seem like a handful at first, but actually it's not that bad. So let's say that this is 0. Then we have -3, -2, and 3. It's going to be useful to find f of 0. F of 0 is going to be 0 plus 2, so it's 2 divided by -9. So 2 divided by -9, that's f of 0. So that's -2/9 somewhere here. -2/9. And the asymptotes. So we draw the asymptotes with dashed lines. All right. The more you do this exercise, the more you get acquainted, and this will really help you at university. Yeah, it will be useful for some tasks in further maths, but this is much closer to university than to A level. And then you draw another asymptote. So the asymptotes are x equals 3, x equals -3. I mean, you have this in A level, but not in such detail. Okay, so y equals 0. And then we'll see that the function is negative and decreasing, and it has 2 asymptotes. So it's going to be like that. Negative and decreasing. So it's positive and decreasing up to -2. So it's going to be like this. That's not. It's positive and decreasing up to -2. It has a 0 at this point. So we can already see that it goes something like this. And then it's positive and decreasing like this. Positive and decreasing. And the only thing that we skipped the point of inflection. So I guess the point of inflection is somewhere between -2 and 0, somewhere here. And finally, we draw the, we sketch the function using Desmos just to check ourselves. Always do that, please. Although when I was at university, we had nothing of the sort. X plus 2 divided by x squared minus 9. And here it is. It does seem so -2, 0. So that's minus 2/9, decreasing, decreasing, decreasing. So the function is always decreasing. It's not continuous, but it is decreasing. And we can draw x equals 3 and x equals -3, just to show that they are in fact asymptotes. Okay, so here you are. That in fact we are correct. One more very important thing that I haven't shown you. I haven't shown you slant asymptotes, and here they are. The next function has a slant asymptote. How do you identify a function with a slant asymptote? It's going to be a top-heavy fraction. If it's a top-heavy fraction, and the difference of powers of the polynomials is 1. So if the power of the numerator is 1 more than the power of the denominator, most likely the function will have a slant asymptote. There are two ways to find slant asymptotes. So on this question, we'll just focus on the slant asymptotes. It has a vertical asymptote. It has a vertical asymptote. Please write down the equation of the vertical asymptote, just so that I understand that you're on the same page as me. Very good. X equals 1. Just one person, or everyone is just thought x equals 1? Okay, vertical asymptote is x equals 1. Then the easy way of how to finding slant asymptotes. Easy way. The easy way of finding slant asymptotes is just divide the top by the bottom. Divide the numerator by the denominator. So x plus -1, x minus 1 divided by x squared plus 2x plus 0. So x squared, x goes into x squared, x times x, so x sorry. What am I doing? I'm doing a different way of dividing, and I mixed the two ways. Plus 2x plus 0. So x goes into x squared, x times x, so x squared minus x, subtract, so there's going to be 3x squared, 3x plus 0. 3x goes into, so x goes into 3x 3 times, plus 3, 3x minus 3, and the remainder is 3. That means we can write, y, which we can write y simply. So y is x squared plus 2x over x minus 1. And we can write this as, using the division, as the result of the division, x plus 3 plus 3 over x minus 1. Right. So what we did, we just simplified the expression. Because it was a top-heavy fraction, we have made it into a mixed number. Yeah. You thought mixed numbers won't ever be useful in maths, and they're not. But 11 over 4 can be written as what, 2 and what about 2 3/4? That's what I did here. This is 11. This is 4. This is 2, and this is 3/4. So I've converted the top-heavy fraction into a mixed number. And an asymptote is what happens to the function when x becomes really, really big. And when x becomes really, really big, this tends to 0. So the asymptote is y equals x plus 3. X plus 3 is a slant asymptote. That's the super easy way of finding it. You know, sometimes it's not possible to do it this way. So I'll show you the hard way, the proper way. If y equals mx plus c is a slant asymptote. Oh, what do you mean? So what I did, I took the original function. The original function is x squared plus 2x. I divided it with a remainder. So this divided by this is x plus 3, and remainder is 3. That's what I did here. So that's what I wrote. And because this term becomes infinitely small when x becomes large, as x tends to infinity, this becomes 0. So we can ignore that term, and the function simply becomes x plus 3. In fact, the bigger the x, the closer the function is to 2x plus 3. Does it make sense, Edward? The larger the x, the closer it is to y equals x plus 3. Yeah, so and you can see it from here. Now, the proper way of doing it, if y equals mx plus c is a slant asymptote, then m is equal to the limit of when x tends to infinity, to infinity of of this f of x divided by x. Okay, so let's see. Limit of x tends to infinity of the function of fx divided by x. So we do 2x squared, so x squared plus 2x divided by x minus 1 times x, so x minus 1. And if I open the brackets, actually what I need to do is no, the opposite of opening the brackets. To find the limit, and this is an incredibly useful skill when you, why doesn't it approach? Oh, it is affected. I mean, but why x plus 3 also approaches infinity, but x plus 3 and x plus 3 plus a very small number are pretty much the same thing. We can say that the function behaves for large values of x, for large values of x, for large values of x, f of x behaves like y equals x plus 3. Because the bigger the x, the smaller the difference between the function and the asymptote. And that makes sense. Right. If then the gradient of that asymptote is this, the gradient of the asymptote is x squared plus 2x that. And to find that limit, x tends to infinity, what do we need to do? Well, we need to take x squared out of the brackets. We need to take x squared as the common factor on the top. It's going to be 1 plus 2 over x. And we take x squared on the bottom as well. And it becomes 1 minus 1 over x. Just double checking. If I open the, oh, no square. If I open the brackets, it's going to be x squared minus x. Oh yeah, exactly. X squared minus x. So if I open the brackets, it's going to be x squared minus x, and on the top is going to be x. Now x squared cancels, and I see that as x becomes infinity, this tends to 1, because 2 divided by x tends to 0, and this tends to 1 because 1 over x is also, this tends to 1 and this tends to 1. So this limit is equal to 1. So the gradient of the slant asymptote is 1. And it is. The slant asymptote is y equals x plus 3. So the gradient is 1. Gradient of the slant asymptote. I'm just going to gradient of the slant asymptote. By the way, I'm just going through the hardest questions of the assignment today. So don't worry, the whole if you haven't seen the assignment yet, it's not as difficult as what I'm doing now. I mean, okay, what I'm doing now, it's not difficult, it's more tedious. I mean, there's a lot of work involved. The questions are not so demanding in terms of work. So don't worry, it's not like you'll spend 17,000 hours doing it. And then is a slant estimate. Besides, you have Desmos to help you a lot. Well, you can't use Desmos in your answer. You have to justify, but at least you can check your answers using Desmos. And to find C would be equal to the limit as x tends to infinity of f of x minus k minus mx. Yes, limit of this. And yeah, let's do it. So f of x minus mx. So we found m, which is 1. So it's going to be x squared x squared plus 2x over x minus 1 minus mx. M is 1, so minus x. Don't forget the limit. So that's equal to the limit of, so x squared plus 2x plus 2x minus x squared plus x divided by x minus 1, and that's equal to the limit of 3x divided by x minus 1. And well, I mean, you do the same thing. It's 3 limit. Can you differentiate the limit to find? Do you mean L'Hopital's rule? L'Hopital's rule is only applicable when the limit of the top and the bottom of the fraction is 0. Sorry, when the limit of the top and the bottom is 0. It's not applicable when they're not zeros. I mean, you could. In this particular case, you could, but I'm not going to do that. I'm going to say I'm going to do it properly, because when you go to university, you can't use differentiation to find limits. They will be very mad if you do, because limits are studied before derivatives, and if you use derivatives to find limits, that's kind of that's going the wrong way around. So 3x, and here you take x out of the brackets, and you have 1 minus 1 over x, and x cancels, and you got 3 over 1 minus 1 over x, and 1 over x tends to 0 because this is an infinitely small. It's an infinitely small value, so this is 0. So 3 over 1, the limit is 3. So and this is the c. So if there is a slant asymptote, and you found it. So m is 1, m is 1, c is 3. So the asymptote is y equals x plus 3. Right, and then you start sketching. So you have two asymptotes. One is x equals 1. X equals 1 is an asymptote. So that's x equals 1. And x plus 3. X plus 3. Okay, I can't afford so much space. X plus 3. This is the other asymptote. So y equals x plus 3. This is another asymptote. And what happens to the function? Well, it looks like when, yeah, the function is going to be like this. Like already you can, because you have the asymptotes, and you know that the function is going to be, oh, actually, you know what? That's not necessarily true. No, it is. It's going to be like that. It's useful to find when x is 0, when x is 0. So it actually goes through 0, 0. It's another useful fact. Goes through 0, 0, and yeah. So something like that. Sorry for the mess. Okay, and checking our answer is y is equal to x squared plus 2x over x minus 1. Ta-da! So yeah, here's the graph. So whenever you see a top-heavy fraction, there's bound to be a slant asymptote. Just a few comments on the next task. The next task is actually also a top-heavy fraction, because if you simplify it, and it is in the examples, so x squared x squared plus 1 over x. So it is going to be a very similar graph, almost identical to that one, just slightly changed. Now, if you see something like that, well, it's going to be incredibly hard to try and analyze this function. So what you need to do is you analyze this function first, and then you see that, well, this is a transformation of this graph. This is simply the this is a reflection in the y-axis of the graph. So all you need to do is you analyze this graph, you draw the graph starting from 0, and then you just copy the graph on the left. Okay, how do I know that I have the shape? Well, it has to go through the asymptotes. Then what I've missed is what I've skipped is I haven't found the minimum and maximum. And you will see that it is decreasing, then increasing, and this is a stationary point. This is another stationary point. These are the zeros. So these are the things that I have just omitted. sorry, just because I don't have time. But once you do these, so stationary points, stationary points here, these are the stationary points. Then you have there's no points of inflection here, but you do have the zeros. So these are the zeros. 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 Then what do you have? You have increasing and decrease. You have intervals of increase and decrease. Increasing when, decreasing when. But once you found the slant asymptotes, you kind of always draw in between them. So there are two possibilities. If you have two asymptotes, so either the function goes like this, or the function goes like this. It always goes between the asymptotes. The hyperbola is a very good example. You have two asymptotes and it's between them. You have a hyperbola in between the graphs. And what you did here is you kind of shifted them sideways. No, you didn't shift them sideways. You kind of skewed the graph. It doesn't have this transformation. Okay, but I hope you understand what I mean. Okay, so this graph here, you have a very similar question in the assignment. One thing you need to notice that first of all, the x is any real number. That means the graph will go from minus infinity to plus infinity. But on the other hand, the range is going to be between -1 and 1. Okay, the range is going to be between -1 and 1 because arcsine. Oh, sorry, between minus pi/2 and pi/2, of course. And well, of course, you can sketch it quickly on Desmos to see what's it going to be. So the range is y is going to be between arcsine. Arcsine is between minus pi/2 and pi/2. pi/2 and pi/2. And let's see, y equals arcsine sine x. Look at that. So what you need to notice is that this graph is periodic. It's periodic, and this is the shape of the graph. You can find the period. The period is 2 pi in this case. Period is 2 pi. So you just find the shape of the graph on the first cycle, and then you copy that cycle over. Can please make a PDF of the board, of the whole board? I guess so. Let's see if I can do save as. I guess it will make a PDF. Okay, so that's it. And maybe you have any questions for me? As I said, I've gone through the hardest questions of the assignments. So I've rushed a bit at times. I'll post the whiteboard in the chat. Right, you're welcome. I'll see you next week. Oh, actually, next week we might have a guest lecturer doing the webinar. This is the author of the math paper, which you're doing. So he might be, he's agreed to take a webinar. So hopefully we'll have a guest lecturer next time.
Wait, I just have one question.
Yeah.
I got confused about one thing about how you found the gradient and the intercept for the tangent, like the complicated way.
The complicated way. So
Yeah.
if mx plus c is a slant asymptote, then this. So this is a definition. Well, okay, there's a theorem. There's a theorem. You just need to find the limit of fx over x.
Is that just a fact I need to remember, or is it?
It is a fact that you will, at some point in your life, you will need to prove. I'm giving it to you without proof. Yeah, it's a fact of it is a fact that you need to remember. Okay.
Does that mean that's also a fact for the limit of x as it approaches infinity for f of x minus mx to find the intercept?
Yes. Well, not in. Well, yes. The intercept. The intercept of the slant asymptote. Yes, this is another. So these are the two formulas which you can use, but at some point in your life you will need to prove them.
Oh, so okay.
Okay.
All right. Thank you.
Right. Welcome. All right. You're welcome. Have a nice Easter. Nice holidays.